Hello, dear professors. Our project is Richter's Predictor, modeling earthquake damage. And here are our team members. This problem is to predict damage levels of buildings caused by 2015 Ghaith earthquake in Nepal, based on the data of their geographical location, construction-related features, and some information about their inhabitants. Since this is a real-life problem, our model can help to improve the construction process to face earthquakes, minimize the destruction and economical loss, and most importantly, save lives. The datasets consist of train values, train labels, and unlabeled test data. In our data, we have around 260,000 samples with 38 features. Features are integers and object types. We did exploratory analysis of data. The first plot here shows the distribution of the target variable. From the figure, we can infer that the training data is imbalanced. The damage grid level 2 has the highest frequency in the label sets. This plot shows the distribution of building age, and we can see the following. There are more than 25,000 records belonging to age 0, which means that it is a new building. Age group 10 holds the highest number of records, and most recorded buildings are built in less than 40 years. There are few buildings with more than 100 age, which can be interpreted as outliers. In this slide, we put the distribution of the number of floors of each building before the earthquake and the distribution of number of families living in the buildings. The top graph shows that two-story buildings suffered the most, while the bottom graph also shows that the most records belongs to the building which only one family lives in. And this makes since two-story buildings are often inhabited with one family. This plot shows the distribution of height percentage, and we can infer that the records are mainly concentrated in the height percentage of 2 to 7. As the distribution of the target variable shows, the damage grid level 2 has the highest occurrence, and it especially appears when the height percentage is 5.
During our data processing, we found that there is no nonce. That's good. They use label encoding and one-hot encoding to reform the categorical features. To generate new features, we first created 5 average features according to geolocation. Then we added a sum feature for each geolocation of buildings with enforced structure. Finally, they use robust scalar to standardize the numerical columns and ensure that outliers won't skew our models too much. Then we split the data. Here, the target variable is damage grade, and the other columns are features. We set the test size to 20%, while random state is 42 for reproducibility. To find the best parameter, we tried several methods. To start with, we applied stratified k-fold and set the number of folds to 5, while random state kept to 42. Then in logistic regression, random forest and XGBoost, we use grid search to find the best parameters. At last, CutBoost was implemented with default hyperparameter search because it's already good. In each model, we tried 2 implementations. We used straightforward with grid search and 1vs rest with best hyperparameters from grid search. Here, we make a table to compare the models. As it's shown on the figure, XGB model implemented by 1vs rest technology has the highest F1 score, which is 0.74 on our reserved test dataset. CutBoost has highest score on driven data test dataset, on the other hand. For many models, the F1 score was increased when they applied the F1vs rest classification method. As a sanity check, we provide these curves to ensure you that models work decently.
Next, we are going to explore feature importance. Here we have the plot of feature importances for one versus rest XGBoost. In class number one, which is low level of damage grade, the most important three features are foundation type 2, average height GO1, and has superstructure mud mortar stone. In class number two, which is medium level of damage, the most important three features are number of mud mortar stone structure in GO1, average height GO1, and foundation type 1. In the third class, which is the high level of damage, the top three features were average count of families in GO1, ground floor type 2, and number of mud mortar stone structure in GO1. To sum up, for every model except logistic regression, F1 score improved after applying the one versus rest classification method. Most important features are related to foundation, age, and structure materials features. The model is pretty applicable to a real-life scenario. For an area with similar geographic characteristics and structural types of building, the model can help to predict how much strong the building could be in facing the earthquake. This analysis can be done before the launch of building process, so it would save a lot of money and lives in future. The analysis show the need of creating the following laws. For example, there should be a certain threshold regarding height of the building. For example, building of 5 floors or higher should be built using strong materials as they tend to be affected the most by the earthquake. Second law, which is at a certain age, buildings should be renovated. Next, we can see that outliers boosted the scores. Actually, when we deleted the outliers, the score dropped. It's a proof that we should treat outliers carefully because if we delete them from the training part, existing outliers in the test part will make problems for our model. We can infer that in our project, CatBoost performed the best according to driven data submissions. Finally, our model is working well and it solves the problem stated at the beginning. However, there are still a big space to make progress. For example, we can try to use target encoding, or generate additional features, or use of more advanced models such as neural networks. At last, here's our result on Driven Data website after submitting the CatBoost model. And thank you for listening.